Hi guys, sorry I couldn't be there with you today. I'm trying this new app on my iPad as a lesson, so be patient with me. I already wrote out the lesson and then I'm supposed to be able to talk over it. I'm not very good at writing on my iPad with my finger though, so excuse the poor handwriting. If at any time it's going too fast for you, just pause the YouTube video and give everybody some time to write. Okay, we're going to be working out of your notes from yesterday. We started with polarity yesterday. We're going to start with intra versus intermolecular forces today. So if you guys could pause this and then take a second to get that out. Okay, intra versus intermolecular forces. These prefixes that you need to think of are intra and inter. Intramolecular forces are within a molecule, okay, within one molecule. Intermolecular forces are between multiple molecules. You may be familiar with those prefixes. For example, interstates run between multiple states, highways that run between multiple states, whereas an intrastate is a highway that runs just within a state. We use water as an example a lot in intermolecular forces. So I'm going to use water as an example. Here, I just highlighted here, those are the intramolecular forces. Okay, intra, within a molecule. So what you might want to write down is another word for intramolecular forces is bonds. We've already learned about bonds, ionic, covalent, metallic bonds. Those are intramolecular forces. Intermolecular forces are between molecules. So here are, I guess I already wrote bonds. Here's an example of an attraction between molecules. So you can see the difference is that it's something holding multiple molecules together. Here is something very important. Okay, you'll want to write this down somewhere in that intramolecular forces or even right under the two boxes. Intramolecular forces or bonds are always stronger than intermolecular forces. Okay, they're always stronger. So the bonds that hold one molecule together are stronger than the forces that hold multiple molecules together. You may want to write next to intermolecular forces that we write those as IMFs. It's just a lot shorter than writing intermolecular forces each time. So bonds are stronger. Now here's an example that might help you make sense of that. In liquid water, you have water molecules that are being attracted together by intermolecular forces. Okay, again, that's a liquid, so you have that L right there. Now, when those water molecules become a gas or they evaporate, you know that they're still H2O, right? They're just a vapor or a gas form of H2O. So here, if you look at a gas, it's still H2O. Oops, sorry. Sometimes it goes a little fast for me. You'll notice here that what I highlighted there in purple, those are the bonds. Those intramolecular forces are still intact. It's just that area that I circled in gray where there are no more intermolecular forces, okay, because they've been broken to make a gas. So bonds are always stronger than IMFs. Why don't you pause the recording real quick, and why don't you talk to the person next to you, tell them the difference between intramolecular forces and intermolecular forces. Okay, next we're going to cover the three types of intermolecular forces. The first is London dispersion forces. Now my hope is after you have done that web quest that you turned in today, is that hearing all this IMF stuff, you're really just hearing it for a second time. So it's going to be more of a review than anything else. So the types of intermolecular forces, London dispersion forces. Right next to London dispersion forces, I want you to write the weakest force. Okay, of all three intermolecular forces, this one is the weakest. After this, I'm just going to go bullet by bullet on your note sheet. The first bullet says what type of molecules experience London dispersion forces, and to give 2 examples. All molecules experience London dispersion forces. Okay, however, they are so weak that it's only noticeable in nonpolar molecules. Okay, so all molecules experience this, but if they experience any other type of IMF, then you're going to see that type of IMF. Nonpolar molecules only experience London dispersion, so those are you'll see London dispersions in nonpolars. I gave 2 examples of nonpolars off to the right there. Hal hydrocarbons, C4H10. All hydrocarbons are nonpolar and therefore experience London dispersion. And then CF4 would be another example of a nonpolar. Now, what a London dispersion force is temporary dipoles that are formed from the movement of electrons. Remember, we tend to think of electrons as stationary just because that's the way that we have always drawn them, right? When I drew these electrons right here that I'm highlighting in yellow, when I drew those electrons, I drew them as stationary because that's how we put them on a piece of paper. Remember, electrons are actually always moving. And so when the electrons move, just naturally you might get a couple more on one end than you do on another. So that end would be more negative, while the other end would be more positive. Now, the reason that these forces are so weak is because they are temporary dipoles. They're temporary positive and negative ends because those electrons keep moving. So once the electrons move again, then you'll have a negative side somewhere else and a positive side somewhere else. So the molecules are attracted to each other. Okay, so here's a picture that I drew for this. Now, I actually think it's going to draw all the writing all over it that I already did. So let me actually erase this real quick. Actually, I'll just talk through it as I go. So you'll notice, again, everything that I've highlighted so far in purple, those are temporary, or those are electrons, right? And we think of them as stationary because that's how we draw them. Now, if those electrons are constantly moving, let's say that maybe at one point over at this end, it's a little bit positive, okay, because some of the electrons had moved away from there, which would make this end of the molecule a little bit negative. Now, if that same thing's happening on that other molecule, this end becomes a little bit positive, and this end becomes a little bit negative, and they're attracted to each other. Now, the reason, again, that they're so weak is because they're only temporary dipoles. Those electrons are constantly moving, so then maybe it switches spots, and this end is more negative, this end is more positive, and this end is more negative, and this end is more positive. Okay, that's why they're extremely weak, and because they're temporary and they're constantly shifting. Why don't you guys take a second to talk right now about London dispersion forces. Make sure you understand those types of forces. And then what you're going to need to do is play the second video for the other 2 types of forces.